Today we are going to talk about the most important aspect of oceanography, or rather we can call it as the heart of the oceanography. It does not mean that the other sections are not important, but this is in particular it is very important for the subject of oceanography. So, we are going to talk about the motion in the ocean, right. It sounds very nice, the motion in this ocean, where we are going to talk about the circulation, the ocean circulation, how the water column in the ocean move here and there, right. So, it is going to be a really a very interesting topic for you. So, if you before going into the ocean circulation, we need to know that the other forces, like it's like most of the material, especially the fluids, that is the air and water, or the liquids and the air, they are in some sort of a motion, especially the air. There are many reasons why the air is in a constant movement, right. They are not stagnant, right. They are always moving. There are many reasons why they are moving. So, one of the reasons is that that we call the differential heating, especially you get the sun when they straight in the equator get the most of the heat, right. When the equatorial region, when they are heated, then air become thinner, then they start moving upward, right. Because of the heat, the air get thinner, and then that will move the air upward. This air not moving alone, but with the water vapors, they carry water vapors to the upper layers of the atmosphere. On the other hand, in the polar region, where which gets less sun's energy or heat and is colder, and that will develop actually. So, in the equator, it will generate a low pressure zone, because of the moving air upward will cause a low pressure zone here. But on the other hand, in the polar region, so there is since it is getting less heat, there is more likely to the air to move downward, like here we call the convergence, the previous case called the divergence, and then the sinking the air to the surface of the earth, right. So, these kind of a phenomenon making lot of circulations, going down, going up in the what call the equator, right. It is just a very simple phenomenon, but it is not like that. There are many different locations on the earth, this kind of a movements we call as the cells, like here you see in that image you can see this kind of a shells, Hartley cells or subpolar, like with different type of cells you can see the movement in atmosphere, right. So, the main reason behind is the differential heating on earth and different places on earth, especially the equatorial and polar region as well as the other regions, right. So, this is very important phenomenon, keeping the air in movement, right, this kind of a cells, right. Now, in general, so as we discussed, the equatorial region get more sun's energy, whereas in the polar regions less energy, right. The reason why the sun's rays coming directly into the equatorial region, right. It means coming in a different angle, because here this important concept here, the angle of incident rays. අපි අර පතන කෝණය කියන එක අහලා තියෙනව නේද? Most important thing is this the angle of that rays that coming into the earth, because in the equatorial region there is less air to penetrate, because you see the distance here, less air to penetrate, whereas in the polar region the same rays has to go a long way in the atmosphere, where lose its energy in the atmosphere. Right. So, in general there is a net gain in the energy in the equator, which means it is warmer in the equator, whereas it is colder in the polar region. So, this is something that you know. Right. Now, there is another thing, that is the seasonal variation on earth. Right. We know that on earth there is something called seasonal variations. Since we are right at the equator, we do not see this seasonal variation, but as you know the polar or the temperate countries, they have really clearly differentiable seasons. Now, the question we have is, what caused the seasons? Right. Can anyone think of what is the reason for the seasons on earth? Right. One would think that that is the distance from the sun's rays is different from one place to another on our earth. So, that is making the seasons. Is that right? Any one of you can tell what are these seasons, why and how they are caused, the seasonal variations? What is the concept behind? What makes seasons on earth? Yes, any of you?
Because the earth is tilted, different parts of the earth receive different amounts of sunlight.
Exactly, very good. Anyone else have another idea? Yes, the reason is that the earth is tilted towards the sun, 23.5 degrees tilted. So, this tilt make the seasons on earth, right. We can take very briefly on here. So, this is the equator, how the equator get the sun's rays. So, here the important things, as I mentioned before, the angle of incidence, because it is more perpendicular in the equator, whereas it's the angle is very different in the other hemispheres, right. So, if it is not tilted, that this is how it's going to work more or less, right. So, we won't get the seasonal variation, but the higher temperatures and colder temperatures in the polar region, it's something that we can expect if there is no really the earth is not tilted. But the difference is the earth is actually tilted. Now, what happened? Right. So, this is the summer for the northern hemisphere, right, because it is tilted towards the sun, and this is the summer for the north pole, and it is opposite for the south pole. It's always the winter and summer is opposite in the north and south poles. And if you look at the other side, right, so this is the winter for the north pole, and that's the same season is the summer for the south hemisphere, so southern hemisphere, right. So, that's how this season work, how the seasons occur on Earth, right? But and other than that, you might know that the movement of the sun, this there are a lot of things now. I think it's in grade 7 or 8, you will learn this concept. You might have learned this in your
The axis of the Earth is an imaginary line on which the Earth rotates. It links up the two poles. Both the axis and the Earth are tilted at an angle of 23.5 degrees during a revolution. The tilting of the axis results in direct sunlight falling on different places during different seasons. This causes variations in the duration of days, nights, and seasons. Relationship between the location of the overhead sun and the seasons. Similarly, the revolution of the Earth and the tilting of the axis results in different angle of the sun during different periods. When the sun is directly overhead, we call this the overhead sun. At this time, the Earth's surface and the midday sun forms a 90-degree angle. Different locations of the overhead sun results in variations in the amount of solar radiation received in different areas and at different periods. Spring equinox on the 21st or 22nd of March. The overhead sun is over the equator. The equator receives the largest amount of solar radiation. At this time, the northern hemisphere is in the spring equinox, while the southern hemisphere is in the autumn equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is spring in the northern hemisphere, where the day is longer than the night. In the southern hemisphere, it becomes autumn, when the day is shorter than the night. Summer solstice. On the 21st or 22nd of June, the overhead sun is over the Tropic of Cancer. It receives the largest amount of solar radiation. At this time, the northern hemisphere is in the summer solstice, while the southern hemisphere is in the winter solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime of the northern hemisphere is the longest in the year, while that of the southern hemisphere is the shortest in the year. Besides, there are 24 hours of daylight at the Arctic Circle and 24 hours of darkness at the Antarctic Circle. Autumn equinox. On the 22nd.
So I hope you got some idea about the seasonal variation. It's going to be a lengthy video, but now you got the idea. Now there is something else that you need to know. That is the very interesting phenomenon on Earth. I don't know whether you have heard about this thing. Did you know that any object moving on Earth, any fluid actually, any like air or water, when they are moving, do you know that their direction change? Especially when they are going very far, their direction going to be changed. Right. And here is the example, like if you are moving from the pole, you will say it's north pole to the, if they are coming to the equator, right, their path, if they keep straight, like if they want to come to this place, if they come straight, they will never reach the place where they want to, right? Rather they will end up somewhere else. Why it is? Because since the earth is rotating, but this momentum or the speed of the rotation is different from one place to another, you know, it's because if it is because it's a sphere, the equator has the highest rate, right? So it should has the highest speed, whereas as you go towards the polar region, the speed will reduce, and at the axis in the polar region, that axis, there won't be actually any movement. Actually, I mean, it will just circulate on around its own axis. There is no big movement, right? So it's become near zero. Because of that, any movement, like any objects moving, will deflect, or the direction will change, right? And this is known as Coriolis deflection or Coriolis effect. I don't know any of you have heard about this Coriolis effect. Have you? Have you heard this term? No. Okay, that's fine. So that is actually something unfortunate, that actually this is something very common phenomenon, but we never looked at this one. So that is anyway our education system, we missing some parts, and especially like if you are a pilot, right, you need to know this one, otherwise you will definitely end up in somewhere else. Right. And if you are like a military person who is like working on a heavy heavy arms like artilleries or missiles, so if you want to find a target, if you don't know the Coriolis effect, you will hit a different target for sure, right? So this is very important, that you need to have understanding about this Coriolis effect, right? So why it is? Because of the Earth's rotation, which in the different locations have different rotation speeds, right? Any movement of an object will change its direction, right? There are some actually you can prove that this Coriolis effect, especially if you are in a merry-go-round, right? So I know that, I think that you have been to you have played on a merry-go-round, right? If you don't, but still like you can demonstrate this concept of Coriolis effect. I'll show you a small video on this later on, right? So what is a Coriolis effect? It is the deflection or change in the direction on any of the freely moving object, and that is because of the Earth's rotation, right? So especially the air and in the water, this is very true, that when you are moving, so the direction going to change from one, right? This concept actually was brought by a French mathematician called Gaspar de Coriolis. So that's why it's we call as the Coriolis effect or Coriolis deflection. And what happened is, this is so unique in the northern hemisphere. Because of this Coriolis effect, the objects deflect or change the direction to the right in the northern hemisphere or in the clockwise, whereas in the southern hemisphere it will be counterclockwise. You know, the clockwise, that the same direction as the clock rotate in the northern hemisphere, but other way around in the southern hemisphere, right? So this can be demonstrated in many different occasions, This is clearly noticed in the cyclones. Right? So, when next time you go to the Google and see the direction of movement in these cyclones, right? Because of the low pressure in the mid or in the eye, we call the eye in the center, it's very low pressure, and the air coming to fill that gap, and that's from air from the every direction come to fill that gap, and ultimately started spinning because every direction is the air is coming and pushing each other, and it start pushing. So, always the direction of this spinning of this what called the cyclone is in one direction in the northern hemisphere, and then on the other direction in the southern hemisphere, right. So, you can watch this carefully. You can go to the Google and see any moment you will see cyclone somewhere on earth, and you can see this difference, right. And this is even you can demonstrate in your home, in your sink. When you open your tap, you see in the center, it will rotate and then before going down the drain, right. But if you want to demonstrate that in the northern hemisphere and the southern hemisphere, this rotation will be in opposite direction, right. So, to experience that one, we have to go to the either side of the equator actually. But more important thing is that the equator, right at the equator, there won't be any movement, because it will be a same. I mean, if you are going in the right in the equator, there won't be any deflection, because it's constant movement, the same speed. But if you go south or north, and you will see this, right. So, let's demonstrate a small video this concept.
In this view of Earth from space, it is clear that the Earth is rotating. However, as an observer on the surface of the Earth, the only indication our planet is rotating is in the observation of the Sun during the day and the stars during the night. Every day the Sun rises in the east and sets in the west, but we are completely unaware that we are traveling to the east at hundreds of miles per hour. So just how fast are we moving? Well, at the equator, the rotational velocity of the Earth is an incredibly fast 1,018 miles an hour. If you were to travel from the equator to about 30 degrees north latitude, the rotational velocity would have slowed considerably to about 882 miles an hour. Well, why? Well, as you walk north or south from the equator, you are actually getting closer and closer to the Earth's axis of rotation. Because the surface of the Earth is solid, the rotational velocity will decrease as you walk north or south from the equator, because you're actually getting closer and closer to the Earth's axis of rotation. To understand this better, let's imagine that we take the Earth, a sphere, and flatten it out into a rotating disk, like a merry-go-round. If you were to stand on the edge of the merry-go-round, the rotational velocity would be large, and you would feel like you're going to fly off. However, if you stand in the middle, the rotational velocity would be much less, and you would feel like you're barely spinning at all. Now, what if we were to have two people sit on opposite sides of the merry-go-round and try to throw a ball to one another? You can see that as the ball leaves the hands of the person throwing it, it becomes independent of the rotation of the merry-go-round, and therefore follows a straight path. But because the person trying to catch the ball is still rotating with the merry-go-round, they are quickly moved out of the ball's intended path. Because the merry-go-round is spinning counterclockwise, this deflection is to the right. If it were spinning clockwise, the deflection would be to the left. Now, to an observer above the merry-go-round, the path of the ball appears straight. However, to people on the merry-go-round, the path of the ball curves to the right of the intended motion. This experiment demonstrates how the rotation of the merry-go-round appears to cause a deflection in the path of the ball. This also demonstrates how air movement on the Earth's surface can be deflected by the Earth's rotation, a phenomenon called the Coriolis effect. How do we relate the effects of the Coriolis force to air motion in our atmosphere? To answer this question, let's first investigate what would happen to a parcel of air that was initially at rest with respect to the Earth. At 30 degrees north latitude, the parcel is traveling to the east with the Earth. But if we were to shove this parcel at 10 miles an hour to the north, what would happen to its motion? We have already seen from the merry-go-round experiment that the ball would be deflected to the right, but why? The answer lies in understanding something called the conservation of angular momentum. Angular momentum is the product of the mass times the velocity times the radius of a rotating object. The conservation of angular momentum tells us that for a rotating object, the product of its mass, velocity, and radius is constant for that system. Well, what does this mean? Think of a ball swinging around on a string. If you shorten the length of the string, the rotating ball spins faster. Angular momentum, however, is conserved because as you decrease the radius or the length of the string, the velocity or the rotational speed of the ball is increased so that the product of the velocity times the radius times the mass stayed the same. As an example, let's consider a ball that weighs 1 kilogram on a string that is 1.5 meters long, spinning at 5 meters per second. When we calculate the angular momentum, we find its value is 7.5. If we shorten the string, we know that the ball will spin faster. So if the radius of rotation is reduced to 1/2 meter, the rotational velocity must increase to 15 meters per second so that the product of the mass times the velocity and radius remains at 7.5. Now, how does all this apply to this parcel that we shoved north? Well, as we moved it to the north, the rotational speed of the Earth will decrease. However, because the parcel of air is actually moving closer and closer to the axis of rotation, its rotational velocity must increase by the conservation of angular momentum. If you were standing at 30 degrees north and watching the parcel as it moved, it would appear to be deflected to the right. This apparent deflection is the direct result of the Coriolis force. What is really interesting is that if the parcel continues to be deflected, it would trace out a path along the Earth's surface that kept its original speed of 10 miles an hour constant with respect to the rotation of the Earth. Therefore, the path of the parcel would eventually trace out a circle, much like the path of this baseball on the merry-go-round. Watch as Amanda pushes the ball out to the center, and it makes a complete circle back to her other side. Some important facts about Coriolis force. First, the Coriolis force causes objects to deflect to the right of their intended path in the northern hemisphere, and to the left in the southern hemisphere. This is why low-pressure systems like hurricanes and extratropical cyclones circulate counterclockwise in the northern hemisphere. Second, the Coriolis force affects the direction of an object, not its speed. Third, the strength of the deflection is proportionate to the speed. For example, the faster an airplane flies, the more the pilot must adjust the flight track to account for the Coriolis force. And finally, the Coriolis force is 0 at the equator and maximum at the poles. To leave you with an interesting fact, the effects of the rotation of the Earth are negligible at very small scales. For example, if a pitcher were to throw a pitch at Wrigley Field to home plate at 100 miles an hour, the deflection of the path of the ball is very small, only about 900 microns, which is about 0.9 millimeters, or about the thickness of your fingernail. However, for an intercontinental ballistic missile, if shot a few thousand miles at 1,000 miles per hour, the deflection is hundreds of miles.
So, I hope you got a better understanding. If you didn't understand the physics, just forget about that one, but everything like the summary, you know that any freely moving object has changed its direction, right? Not the speed, but the direction change because of the rotation of the Earth. This is very significant as you go far or further. This won't affect very much in a cricket field, like it's just 60 meters or something, and the deflection may be just like less than millimeter. Usually it's like in every 300 meters it should change like 1 inch, sorry, every 300 feet it will change like 1 inch or something like that, if I memory is right. So that movement, but as you go further that will affect greatly. Now the question is, how does affect to your day-to-day activities? Like this is not a big issue for us for our day-to-day activities, but as I mentioned before, this is very important for a pilot, right, where they are moving, like in this case, if someone like this flight is moving from here, right, that targeting this straight line to here, right, but definitely he will ended up in somewhere there because of its deflection clockwise, right, it will rotate to the other side, right. And then if you are coming from the north to the south, right, again it's the clockwise, you see, and then it will deflect, right. So if you are a pilot, you definitely need to know about this, as I mentioned before, right. So otherwise definitely we will end up in somewhere else, not the target, as you as you can see is the actual flight direction, and the target will be very different from one another. Now why do we learn this one for the oceanography? That's something that we need to think of. Does it anything matter to us? Yes, because any fluid, it's maybe water or air, will be affected from this Coriolis effect is very much, especially the ocean circulation. This circulation in the ocean as well as in the atmosphere is highly influenced from this concept of Coriolis effect. So you need to have some basic understanding. That's why I put we will talk about this, right. So with that knowledge in mind, let's move on to our main topic, the motion in the ocean. We are going to discuss about the waves, the currents and the tides as a main form of motion in the earth. Right. You might, I don't know whether you know about the differences, or do you think are they same, the waves, tides and currents, are they same or something different? So let's dig into further on these aspects, right. So as you would see here in the images, two images here, top one showing the atmospheric circulation or the air circulation, in which direction usually the air flow in the top image, and the bottom image it's discussing about or showing you the movement in the ocean, or the ocean currents. So if you look at the very closely, you see the movement, like here you see, or here, and you look at the movement in the atmosphere in the same area, right, like here it's clockwise and it's same, and in the southern hemisphere, in the southern Atlantic Ocean, it's anti-clockwise, right. It's always like that in even the Pacific, even in the Indian Ocean, right. You see this kind of a pattern. You see the ocean circulation, especially the currents, it reflect the movement in the air or in the atmosphere, because there is a link between the atmospheric circulation and the ocean circulation, which on the other terms, the ocean circulation is affected by the wind circulation or the atmospheric circulation. But what else? There are many other factors that affect the ocean movement. Mainly the heating that we discussed at the beginning, the sun's heating or the solar radiation, the solar heating is that expand the fluids like air or water, and that will make some hill formation, and like some because of the expansion it will start moving in a small scale, right. The second thing is the wind, as we discussed. Wind is one of the main reasons why the ocean is circulating, because of the wind force, right. The gravity is another thing. Definitely gravity is affecting the movement of the water column in the ocean, and the last one is the Coriolis force or the Coriolis effect, right. So this is again affecting the direction of movement, but not the speed. Right? The any current movement, the direction will change because of the Coriolis effect. Right. So, these are the main factors that affect the ocean circulation. So, let us dig further into this ocean movement. Now, there is another thing that you might not heard, right? That is the direction of the ocean movement. Right? So, as example here, you see the wind direction. You can see in the purple arrow showing the direction of wind. So, we will say it is from the north to the south, more or less, but you can see the movement in the ocean is different, or is an angle to the wind direction. Right. So, wind is blowing here in direct direction, but the ocean flowing in some angle to the wind direction. Right. And this is because of that, again the Coriolis effect, right, because though the water is trying to move in the direction of the wind, but because of the Coriolis effect, that this the direction of movement will change. But now the problem is, like, it is the huge or the large water column, the movement of the water column, like each molecule in the water column will be trying to move in a different direction because of the Coriolis effect, but so it will get a sort of a net, or the direction will be decided by the net force, right. So, again you do not understand the physics, just forget about that, but what you need to know about is that one of the main reason why the ocean is circulating or moving is the wind, but the currents or the ocean circulation will be into an angle from the wind direction. So, if you know that one at least, and that main reason is the Coriolis effect due to the earth rotation, right. So, that is the concept that you need to know. At least you understand that concept, then you can explain many things, right. Now, if you want to like make it so clear why this what is the angle of the movement, then you have to go for you need to explain little bit of using the mathematics, right. But you have to use the vector analysis, in the mathematics we talked about the vector analysis, right. So, do not again take it very seriously, but just to understand what is happening here, and then because of this Coriolis effect, there is something else happening. It is called the Ekman transport, right. What does mean the Ekman layer or Ekman transport? Again, this theory was brought by the scientist called Ekman. So, that is why I call the Ekman transport. So, what is he is explaining here is, as you can see in this diagram, it is called the Ekman spiral or spiral. This is the wind direction. As you can see, the direction of the water is an angle to the wind direction, right. How it happens? In the surface layer, you see in the surface layer, you imagine that the water column is made of thin layers of the water, and the surface layer get the maximum wind power, right. It trying to go straight because if this wind is the power for dragging it. So, in the surface molecules trying to go straight because of the high wind power. Now, the problem is this surface layer is attached to the second layer, right. So, the second layer has less power than the top layer. So, it is trying to go like that, and it has to drag the bottom layer as well, and it has to turn a little bit because of the slow movement of the layer below. Likewise, all the layers are connected to the one above and one below, right below. Because of that, the actual direction will change gradually, right, and eventually it will make something like a spiral, right. So, again, if you do not understand, just you can forget about that, but one thing you have to remember is that the movement of the ocean will be to an angle to the wind direction. So, you know that one. Now, you see, if the depth is enough, sometimes the movement of the water column may be even opposite direction. If the Ekman spiral or Ekman concept is right, even the water movement can be a opposite direction to the where the wind is flowing, right. So, mathematically you can explain this as like this, form the vectors, right. So, let us move on, right. When we are talking about the ocean circulation, we are talking about two major phenomena related to the ocean circulation. Right. We call the surface circulation, right. That is happening in the surface layer. Right. Surface means that not just the top of the ocean, but like a few meters or few hundred meters of the ocean will be in motion because of the wind effect. Right. Wind will not affect the bottom layers, like if it is like 500 meters or 1000 meters, the wind not going to affect. But in the surface layers, the wind going to affect, and because the surface circulation is mainly from the wind, we call it as the wind driven circulation, or the surface circulation, or the wind driven ocean circulation. Right. The second type of the ocean circulation we call the deep circulation, that is the movement in the water column in the deep ocean. And deep ocean movements are actually mainly because of the density differences, but not the wind. So, wind is not going to affect the bottom, but any density differences in water in the top layers and the bottom layers will result in the movement of water columns in the bottom, and we call this a deep circulation. The reason behind the deep circulation or the density driven circulation, as the other name it calls density driven, right. So, the density will change because of the temperature and salinity. The temperature going to affect the density, as we already know. The other one is the salinity. If the salinity differences will cause the density differences, or because of both the temperature and salinity, there can be some ocean circulation which called the density driven circulation, right. So, basically now you know that there are two type of ocean circulation, the surface circulation mainly wind driven, and the deep ocean circulation or density circulation, but there are other circulations as well which we will discuss. And because of the deep circulation is density driven, or we call the temperature and salinity driven, we call this as the thermohaline circulation. Thermohaline, thermo is temperature, haline is the salinity, something to do with the salinity, and thermohaline circulation, right. So, this is not something complicated, right. You can understand that thermohaline circulation. Right. With that, let us move into the one of the well known something on the ocean that we all know, that is the waves. What are these ocean waves and how they are formed, and how they impact us or even the marine organisms, and what is the importance of the ocean waves. So, let us discuss the ocean waves. Right. So, as we all know, the waves are like, we know very well about the sound waves, which is the way of moving the sound signals, right, in the air or wherever. And there, you know, it's the energy is moving, but not any particles are moving in a sound wave, right. I hope you remember this when you, in your school time, you learned about this, the sound waves. It's only the energy is moving there, but not any particles are moving, right. So, similarly, the ocean waves, the waves are actually called the rhythmic movement, the same as the sound wave. They also carry the energy, but not the particles, right. On the other sense, waves, they do not really move in the particles, but only the energy, right. We will try to understand this a little bit further, right. So, so as we know already, the main reason for the surface water movement is the wind, right. So, wind causes the movement of surface waters, including the waves, right. But as we know, there are other reasons as well, which we will discuss later on, right. So, how these waves are formed? You might have seen some waves are like very low, has less energy, whereas some waves can be like, there can be mighty waves like a wall of water sometimes. As you can see in this image, you can compare a man on surfing in this gigantic wave, right. So, you can't imagine how they can affect this big waves on this kind of a person who is doing surfing as a sport or adventure, right. But of course, you need a lot of training to do surfing on this kind of a situation, but this kind of a huge wave can be seen, right. Again, we have a small video, we see that one and then we'll come back.
What causes waves? Well, it really depends on, hey! Not that kind of wave. I'm talking about water waves. It's good to remember there are many kinds of waves. There are sound waves, which are caused by oscillations in the air. There are light waves, which are carried by speedy photons. And there are water waves, which you find in bodies of water, like the ocean. These are the waves we're going to talk about today. The regular waves you find at the beach are caused by the wind. This might seem strange, since the waves keep coming even if it's a calm day. But these waves are made by more than the wind right here. They're made by the wind blowing across the entire ocean. And the ocean is huge. If you were able to walk on water, it would take about 76 days to walk from Los Angeles to Tokyo. So even if the wind is not blowing here at the coast, you can be sure it's blowing somewhere across the vast ocean. The blowing wind scrapes across the surface of the water, giving it a bit of a push. The energy from this push is passed along to the water. There are different factors which determine how much energy has passed from the wind to the water. Is it a strong wind or a weak wind? Is the wind isolated or spread out over a large area? And how long does the wind blow? All of these things play a role in just how much energy is pushed into the water. This means that even when the weather is perfectly calm at the beach, you might see giant waves if there's a storm out at sea. There are other waves which are more rare and destructive: tsunamis. Tsunamis are not made by the wind. They're made by a massive displacement of water. For example, when you get in the bathtub, you displace a lot of water and make waves. You're making teeny tiny tub tsunamis. It takes a massive event to displace enough water to cause such a gigantic wave in the ocean. One possibility is an earthquake. For example, the Boxing Day tsunami, which struck Southeast Asia in 2004, was caused by an earthquake, which measured 9.1 on the Richter scale. At the bottom of the ocean, two tectonic plates slipped. A 1,600-kilometer section of the ocean floor shifted up about 15 meters. This lifted the water above it, triggering the wave. A similar catastrophe struck Japan in 2011 when a 9.0 earthquake occurred offshore. And while tsunamis are destructive and terrifying, luckily they are rare. Another way to displace massive amounts of water is by dropping a huge object in a body of water. You may have seen this when someone cannonballs into a swimming pool. The result is a series of large waves which can be awesome or annoying depending on your point of view. Something similar caused the tallest recorded wave, the mega tsunami in Alaska. In 1958, a large earthquake caused a landslide into Lituya Bay. The mega splash caused a wave over 500 meters tall. Surf's up. Dude, I don't think so. No. In addition to earthquakes and landslides, there's another source of tsunamis: space. Outer space is teeming with large rocks. Occasionally an asteroid will find itself on a collision course with Earth. And since over 70% of Earth is covered by water, the odds are high that it will land in the ocean. When it does, depending on its size and speed, it can displace a huge amount of water and cause a massive tsunami. So the next time you're at the ocean, take a moment to think about all the different ways that waves are created. There are the peaceful waves created by the ocean breezes, the tsunamis created by earthquakes or massive landslides, or asteroids plunging towards the Earth with a terrifying momentum. I used to be able to relax at the ocean. The ocean is filled with countless fish. Not one of them has subscribed to our channel. This is your chance to show the fish what they're missing. Subscribe today and show them marine life why we are on top of the food chain.
All right, hope you got a much better understanding about the ocean waves, different waves, the causing the waves in the ocean. So I don't want to go into very details. Just like the sound waves, same as the sound waves, like we can talk about the crest and the trough, and you know about the wavelength, the wave height, right? The wave height and the wavelength, and the frequency, like how many of them within a second, right? And the wave period is the time taken to pass one crest to another crest or one trough to another crest, right? So you know all these things. The crest, the trough is the highest and the lowest, right? You know all these basic concepts. The wave period, the wave speed, right, and all this, the steepness, that's the wave height divided by the wavelength, the frequency and amplitude. That's everything apply to the ocean waves as well. But here we don't want to go into that detail. What we really need is like how the waves are generated in the ocean, and why they are different from one place to another. As the video explained, you see the waves are mostly generated from the wind, but of course there is other causes. But if we consider as the wave generated, so wind generated waves, So they are not really just because of the wind in that particular place, but maybe it's far in the distance in the ocean, but it's like a net effect from the ocean, the atmospheric circulation, right? It's not just like the wave wind because of the wind in that area, right? But anyway, the wind is the main generating force behind the wave, right? Now, how actually they are formed, and you can explain this with little bit of a physics, right? It's like this. If there is no any wind, the ocean will be very flat. There won't be anything, right? Just like a cup of water in your glass. You won't see any wrinkles. But if you are in a lake or even in a pond where it's directly exposed to the wind, you will see these kinds of small wrinkles. We call them wrinkles, right? Because how these wrinkles are formed, because wind is trying to drag this water, right? Wind is trying to drag the surface water, but there is a force against that. It's called the restoring force. That is because of the surface tension. That's why we talk about the surface tension in the previous lecture, because the water molecule has higher surface tension, which means when the wind is trying to drag the surface water, the surface tension trying to restore that one. We call the restore force. In that restoration, actually start to form small wrinkles like this, small like a wavy something. Now what happened? If still the wind is blowing, now it's not like the surface is not smooth like before, now it is bit rough. Now the wind effect on this rough surface is higher than the smooth surface. Now because of still the wind blowing, and because of these wrinkles, now the resistance is higher and start to drag, and surface tension will be even stronger trying to restore this one, right? And the wrinkles will be even higher, like it's gradually these small wrinkles become waves, right? It's in very simple terms. This is how the waves are formed, right? And then you can look at it here too, like you will see wrinkles or small ripples, like a small wavy like things, and it will gradually increase. And when come to the surface, to the beach or the surf zone, you will the highest waves, right? When you go to the beach next time, you watch carefully. From the distance, you will see only a small movement in the surface, but when they come to the surface or to the beach, you will have the highest wave, right? So you can observe this next time, right? Provided that there is no COVID, that you can enjoy the beach, right? So that's how these waves are formed. So you can see it in here as well in this image. Initially in a map view as well as the wave profile, as you can see here. So like it will be more wrinkles or wavy in the beginning, and eventually they will make a bigger, higher or stronger waves when they approach the beach, right? So that's how the waves are formed in the ocean, right? In this image also it's showing that in the far distance you won't notice even these waves, but when they approach the beach, they will increase gradually. Okay, so that's how the waves are formed, right? So what really happened in this wave formation? Does it really move in the particles? That's something that we need to consider, right? So how these wind generated waves are formed? So what happened during the movement, right? But before that, what does really affect the wind generated waves, right? What is affecting to cause the wind generated the waves? Of course, the velocity of the wind. That's very important. If the velocity is high, you will have higher or stronger waves. Especially if the wind going to blow for long period of time, then you will have higher waves, right? The other one is the velocity and the duration. The second one is the duration. If it is longer, if it is higher, it will be stronger, and if it is a duration is high, you will expect more longer or higher waves. Now the third thing called the fetch, right? I think you haven't heard this word as well. Fetch is the how long the wind can blow without any obstacles, right? Of course, in the ocean there is no many obstacles, so then the wind has the fetch is very high or lengthier in this ocean, since there is no any barriers. That may be very different, like in the bay or like in the lagoons, because there can be barriers, then the fetch is smaller. But if the fetch is higher, then you will expect a stronger waves. And the other thing is the state of the sea surface. We call the state, that what is the present situation. If it is already like a stormy, then you can expect even higher waves, right? If it is like a very calm, and if it is started wind blowing, then you will expect a small waves. Like, so these are the key characters that will be affecting the waves in the ocean. Just like in the image, like a calm wind will cause smaller the waves, right? In this condition, usually in Sri Lanka, in the fishermen, they call like the sea is like a river. Ganga wage kiyala kiyana muhuda, right? It's like a river, because just small wrinkles, there is no waves at all, right? Sometimes we will experience the ocean like this, if you are lucky enough, but not always like this. But in many cases, the ocean will be like this, right? Like called the stormy wind. If the wind in different directions, very strong, right? And you will end up something like this, like even the direction of the wave will be changed constantly, and then that will really make it uncomfortable. Like if you are in a boat in this situation, you are going to will be really disturbing, especially if you are not very not used to sea conditions, right? Okay, so we talk about this fetch, sea state, and different things, that how they are affecting the waves, like the wave height, the wave length, and all will be different from one another based on these differences, right? So keep in mind that one. You see the different wave formations sometimes can be like this, very calm conditions, right? Whereas you will experience this kind of like a stormy condition, we will have a different conditions, right? Calm versus stormy, right? And these are very important, especially if you are like an oceanographer, you want to experience the ocean or do some research. If the ocean like this, you are so lucky, so you won't have any difficulty, you won't get something called the seasickness. Have you heard about something called seasickness? like if you are not used to the ocean conditions, even if you are used to, but if you haven't gone to the sea for some time, then you will get something called the seasickness. You will feel very drowsy, you will be vomiting, you will be very tired, right? And personally, we are experiencing quite often, since we are going to the sea quite often, and many students also sometimes join with us to go to the sea, and especially they are coming to help us, but unfortunately in many cases we have to help them as well in many different ways, because they can't stand in these conditions, right. So we have to take care of them as well, right. So but anyway, it's not always like that, it can be very different. So again, with wave height and see the everything depend on the many different factors as we discussed before, right. Now the important thing is, as we discussed before, how the water molecules move or the particles move in a wave, right. To demonstrate that one, we can like in this graphic you can understand the movement of the particles. Like if you put a bottle in the ocean wave, like it will just move like that, it will tilt to one direction and another, right, and it's not really moving, it will just tilt to either side, and it will stay the same. And on your left you can see the particle movements actually in a wave. I mean the ocean wave, actually the particles movements will be a circular like this. It's like a vibrating, particles will be vibrating on a circular pattern, like in here you see in the bottom the circle will be very small, and when it comes to the surface, the movement of the particles will be, the circle will be higher and higher, and that is how we get these waves. You see in the deeper waters it is not obvious, but when they come to the surface, that is how the water molecules all together move and make a crest or trough, right. This wavy formation is actually because of that the circular movement, right. It is perhaps a bit difficult to understand, but of course if you are good in physics, all these are actually learned in your physics subjects, but if you do not understand, again forget about that, just need you just need to understand the basic concepts anyway, right. So it is very important to know that it will be a circular movement in the particles, but not actually the bottle will be moving. But how about if you throw a ball into a wave, haven't you seen that it will come to the surface, right? You might have seen it might come to the surface, but that is something different, right. It is not only the waves, but there are some currents as well, which we will discuss later on. If you are like a fit swimmer, if you can go to a little bit deeper into the ocean, at least if you can pass the waves little bit, and if you stand there, you will notice that when the waves are come, if you just like jump up or jump higher, the wave will pass you and you won't go anywhere, like you can still stay without any movement, like you just need to push up and then you won't move, right. You might have seen this one when you are playing, right. So if you ever had a chance to go to the field, you will know these things because we could have done these things, but anyway, so that is how the particles move in the ocean. There is a video also describing the same concept, but I do not want to I will put it in the LMS side. As you can see, this is how the particles move in a real time in a wave, and that's how these waves are formed in the ocean, right? See, at the depth about equal to the half the wavelength, the motion stops, right? So, the half the wavelength, then there won't be any the motion in the particles, which means the wave will be only affecting the half the wavelength of the wave, right. So, not anything below. So, keep in mind again when we will discuss this further when we are discussing about the tsunami waves. So, tsunami won't affect the bottom waters, even they won't affect very much in the deep waters, but only in the when they come to the beach, they will have the highest effect, because that is because
We hear about strange things from distant places being washed up on our shores all the time, but how do they get there? Ocean currents are the movements of surface water in the oceans. Their direction is influenced by many factors, including the rotation of the Earth, the size and shapes of the continents, the prevailing winds, and even water density. Ocean currents caused by prevailing winds are called drift currents. In the northern hemisphere, the circulation of the oceans is clockwise, and in the southern hemisphere, the currents are anti-clockwise. Currents originating from the polar regions carry cold water. There's the California current, the Peru or Humboldt current, the Labrador, Canaries, Benguela, the Antarctic circumpolar currents, and the Oyashio. Currents originating from the equatorial regions carry warm water. There's the Gulf Stream and North Atlantic Drift, the Brazil Current, the North and South Equatorial Currents, and the Kuroshio. So perhaps it's not so surprising that many of the items that are washed ashore originate from far-off places, thousands of miles away.
Right. So, that explain a little bit of why actually some like the bottles and all wash to the shore, if the waves are not moving any particles, but they do carry some stuff to the beach because of the currents. It's not really because of the waves. So, keep in mind. So with that, let's conclude today's session. We will talk a little bit further next week, like what are the different types of waves and how they are formed in the course, right. So